All right, so in letter C, what's the variable or what's the number we're plugging in for x? 4, and the number we're plugging in for y is 9, and then we're just following the order of operations. So this is going to be 4 times 4, and then we're going to subtract 9, and the right-hand side is going to stay as a 6. Remember, as we are showing our work, we're doing one line per step as our order of operations. So we're going to begin with multiplication before subtraction. 4 times 4 is 16. And then we're going to subtract 9, and that's equal to 6. If we take 16 minus 9, that leaves us with 7 is equal to 6. So did we produce a true statement? No. So as a result, we should be able to state that 4 comma 9 is not a solution. Okay, again, we want that ordered pair as part of the answer there. Okay, don't just put it, it's not a solution. We're stating that the ordered pair 4 comma 9 is not a solution. All right, and then for letter D, what are we plugging in for x? -2, so we've got 3 times -2. What are we plugging in for y? -4. And the right side should be equal to 10. Again, I'm fine, even in order of operations here, since both of these are multiplications. If we do both of those, then we'll move to the subtraction next. 3 times -2 is -6, minus, if I take 4 times -4, that's going to give me a -16. All right, we saw this one earlier. When we are subtracting a negative, this now becomes a plus a positive. And if we take -6 and add 16, that gives us a positive 10. And on the other side, we'd still have positive 10. Did we produce a true statement? Yes, we did. So as a result, we should be able to state that -2 comma -4 is a solution. All right, questions on work, answers, anything like that, then we're going to expect you to be able to do. Again, I want to be very deliberate in what we're doing and why we're doing it, because these ideas are what's going to help us as we move into example 2A and 2B today. Okay? Last chance. Any other questions? Okay. All right. Now, we're going to go ahead and flip this back over, and we've got some more vocabulary words that we need to define before we move into our second example of the day today. So, we're going to talk about what the graph of an equation with two variables means. Okay, we're going to talk today about how to make them, but here is one of my biggest pet peeves as a math teacher. When I try to build off of prior knowledge and I find out that students don't have prior knowledge, at least at the level that I want, because they don't draw the connections that we're looking for. Okay, so here's a big, huge thing. Like, I can't test this on paper and pencil. But for you to get to where you need to be with your level of understanding, this definition here is going to play a vital role in getting where you need to be. Okay? So, I'm going to throw up a problem and I'm going to give you something to consider before I give my definition of this. Okay? I'm not going to give you an ordered pair. I'm going to just give you an equation. And in this equation, we're going to say x plus 3y equals 12. Okay, now we just got done practicing this 4 times with an equation that has 2 variables. Here's what I'd like you to do, and you can do this with somebody that sits next to you. You can kind of have a conversation back and forth with this a little bit. I want you to give me an ordered pair, an x and a y value, that make that equation true. I'm not asking you to test one. I'm asking you to give me one. Okay? Talk with somebody next to you and explain why you think your ordered pair, remember that means you have to give an x and a y value, why you think your ordered pair is going to produce a true statement. Okay? Go. Right? Again, I want an ordered pair that if I plug it in will make that equation true. Okay, we're just asking you to think about what you just got done doing, but you're coming up with your own ordered pair. Okay, about 30 seconds, wrap up your conversations. You guys talked about this, right? Okay, so if you don't have one, perhaps use the resources that are sitting right? Okay, so like that's my key. So you guys should actually take one another and start talking about how else I can make that all work. Do you have one? Maybe 6 and 6. Okay. Do you guys both agree? All right. So again, let's see what we can all come up with here. All right. So we're going to start in the back table, and I want you, if you guys came up with different ones, that's fine. Okay. If you came up with the same one, that's fine. And then as we go through, I don't want you to like duplicate. So once we've got one answer, let's keep that one answer. So Chloe K, did you come up with an ordered pair that made this true? What was it? 6 and 2. Okay. Now we should always be able to double check your answer, because if we were to plug this in for X and plug this in for Y, we'd ask ourselves, does it produce a true statement? So if we plug 6 in for X, this is 6. If we plug 2 in for Y, this is going to become 3 times 2, which is 6. And what's 6 plus 6? 12. It's 12. So this one is a solution. Okay, Quinn, what'd you come up with? Negative 6 and 6. Now, if we plug negative 6 in here, this is just negative 6. What's 3 times 6? 18. And what's negative 6 plus 18? It's 12. So there's another solution there. Okay, Delaney, did you come up with a different one? 3 comma 3. If you plug 3 in here, that's 3. And 3 times 3 is 9. And 3 plus 9 is 12. There's another solution. Jaquan, were you able to come up with another one? No. Chloe? You had 3 and 3. Okay, that works. Francisco, did you have one? No? Serena, what did you have? You had 3 and 3. Miles? 0 and 4. Perfect. If you plug 0 in for X and you plug 4 in for Y, 0 is 0. 3 times 4 is 12. And 0 plus 12 is 12. There's another solution. Okay, Ron, did you come up with one? 6 and 2. 6 and 2. Okay. Megan? That's fine. Go ahead and tell me what you had. 6 and 2. You had 6 and 2? 9 and 1. If you plug 9 in for X and you plug 1 in for Y, 9 is 9. 3 times 1 is 3. 9 plus 3 is 12. There's another one. Kane, did you come up with one? Negative 3 and 5. Negative 3 stays as negative 3. 3 times 5 is 15. Negative 3 plus 15 is 12. That's another good one. Evan? All yours are up there. Cynthia? Those are already up there? Hayden? Yes, Abby? All right. Anybody else? Miles just said, like, he just came up with one. Anybody else recognize one that's not up here? Okay, would 12 and 1 work, though? Because 12 would be 12. 1 would make this a 3, and 12 plus 3 would be 15. You're close, but it's not 12 and 1. 12 and 0. If x is 12 and 0 is, or y is 0, this becomes 12 plus 0, which is 12. So 12 and 0 is a solution. Okay? 12, but 12 and negative 3 won't work. Because if x is 12 and this is negative 3, that would be 12 plus negative 9, which would actually be 3. So here's my question, though. The reason I like coming up with this is there just one answer? No. What we see is there's a lot. And in fact, there's more than a lot. There's an infinite number of them. So like when some of you go, well, I didn't come up with any, that's fine, but like literally, there's an infinite number. You could have picked any number you wanted for x, and you could have found the y value that you needed it to be. It's not like there's 7 or 5 or 4 right answers. There is an infinite number of them. We can continue with this list forever and ever and ever and ever and ever. Never running out of them. Now, that being said, can I pick whatever I want and it works? No. Here's an easy one to show. If I picked 1, 1, would that work? No. Because this would be 1, this would become 3, and 1 plus 3 is not 12. So we have an infinite number of things that work, but that doesn't mean everything works. Do we understand the difference there? Okay? Now, why am I bringing this up? Because this is going to lead us right into our definition today. And this is the big idea. Like when I ask my students to graph an equation, I'll be honest, as an algebra student, most of them know how to graph it. They can't tell me what they're showing me though. And that's my frustration. Like they don't understand what it means. Hey, Mr. Tompkins, you taught me this process, and I've memorized that process, and I've gotten really good at it, but don't ask me to tell you what any of that means. That's the problem. To build off of that, you have to know what a graph means. This definition here is going to be pretty significant. Okay, so let's get this jotted down here correctly. So, the graph of an equation in 2 variables is the set of points in a coordinate plane that represent all the solutions of an equation. So today we're going to focus on graphing equations. That's like the big idea that we have. Okay, that's the next standard we're going to talk about, graphing using tables. Okay? And like I said, some of us, we're just going to learn this is what Mr. Tompkins wants me to do, and I can graph an equation. What I really want you to be able to do is graph an equation and tell me what's significant about it. This is the significant part about it. Okay? There is in the coordinate plane, if you think about all of the x and the y-axis moving on forever and ever and ever in all directions, there's an infinite number of ordered pairs. Would you guys all agree with that? Okay? We're showing you mathematically which ones make an equation true. So when I ask you to graph this equation, which is something I'll ask you to do here in about a week, okay? you will be producing all of the ordered pairs that make this equation true. So we're not to this point yet, but when I ask you to graph this equation, you're going to come up with all of these ordered pairs on your line. Okay, you're going to be showing it, not just all of them, like you're going to show all of them, all infinite number of them. If that line kept going on forever and ever and ever, you would show every solution in that problem. Okay? So that's what we're trying to do. We're finding a way mathematically to represent all the solutions of an equation. And that's exactly what a graph of it is. Okay? Now I got two more definitions here. Okay? A linear equation. This is a huge vocabulary term, especially when we get into Algebra 1. Because when we get into Algebra 1 and we ask you to graph an equation, my Algebra 1 students are going to find out that there's a lot of different ways graphs can look. When they hear the word linear, they love it. Because they know exactly how it should look, and they know exactly how to graph it. When it's not linear, not nearly as nice. Okay? Here's what a linear equation is. This is an equation whose graph is a line. A linear equation whose graph is a line. What is nice about that? Well, not even always straight across. It could be diagonal. It could go this way. It could go this way. It could go this way. But ultimately, how many points do you need in order to draw a line? You need 2. So I'm not going to have to graph an infinite number of points. I'm going to be able to find a couple of them, and from that, be able to draw my line. Okay? Give me a minute here, but I'm going to show you what happens when we graph these points. I'm going to leave them up here for a minute. Okay? All right. Now, you might say, Mr. Tompkins, you have a typo. You have linear equation twice. No, I don't. I have a linear equation once, and I have a linear what? What makes a function a function? Each input has exactly one output, or it passes the vertical line test. There's a reason that these are different. The first one says it's a linear equation. That means that it can be anything that looks like a line. The second one says it's going to be a linear function, which means it's going to be a line and a function. So that's not a duplicate vocabulary term. It's telling us something slightly different there. It means it can't be like this. It could be horizontal, but it can't be vertical is what it's going to tell us. And that's exactly what we're going to add in here. This is a function whose graph is a non-vertical line. And the reason it can't be vertical is because then it wouldn't pass the vertical line test. But otherwise, my line could look like this. My line could look like this. My line could be horizontal. The only thing that this eliminates is it can't be vertical. Because if it's vertical, it's not a function. You might say, well, Mr. Tompkins, what is it? Well, then it would be a linear equation. And yes, we're going to be graphing those here tomorrow. But for today, we're talking about linear equations and linear functions. Now, before we move into the next example, I want to show you what happens here. You guys did an excellent job of coming up with multiple solutions for this particular equation, okay? I'm going to flip to the back page of my notes here where there's already a graph, and I just want to show you something. You don't need to actually do this, but I want to show you what's going to happen here. If you were to take all except this last one's a little too big to fit on my graph. If you were to take all of these points and graph them, I want to show you what happens. When we graph 6, 2, that tells me to go over 6 and up 2. Okay, when I graph negative 6, 6, that tells me to go, hold on there. Yeah, 6, 2, and negative 6, and 6. tells me to graph that point right there. Okay, when I graph 3, 3, over 3 and up 3 is going to tell me to graph right there. When I graph 0, 4, I'm going to graph that point right there. When I graph 9, 1, that's going to tell me to go over 9 and up 1. When I graph negative 3, 5, that's going to tell me to go back 3 and up 5. What am I starting to create here? I'm starting to create a line. I'm creating a linear function. Because that's what that graph shows. It shows all the solutions of an equation. If you were to graph 12, 0, which my graph isn't quite big enough, you would see that it actually comes right over here. Okay? This is why I'm telling you there's an infinite number of solutions. Here's another one that you guys didn't come up with. Negative 9, 7. If I made this negative 9, and this 7, 3 times 7 is 21, if I add those two together, I get 12. This is what I'm telling you. You could come up with an infinite number of solutions. But it's kind of cool that you guys came up with some that if you transfer them over to a graph, you start to see that it traces out that line. Okay, that's the big idea that we want you to get. Now, let's get to example number 2. Okay, and this particular standard that we're talking about today is graphing using tables. So for example number 2, we're going to ask you to graph each function by completing a table of values. Okay, anytime I ask you to use a table of graph, I am expecting 5 values to show up in your table. And then you use those 5 values to graph it and complete your function. Okay? Now, here's where you're going to have some trust. Does it matter which values that I pick for my table? The answer is no. So I do not expect any of you to automatically have the exact same table that I would create. But I am going to give you some suggestions that I have to help make your tables easier to make. Okay? So ultimately what I need you to be able to do is I need you to be able to come up with an x and a y value that are going to make this equation true. Okay? Now, here's my suggestion for you. When it comes to creating a table of values, I would always suggest that you pick positive and negative numbers. A lot of people just like positive numbers, but that sometimes is going to cause you issues. So I always tell people pick positive numbers, pick negative numbers. Also, I would pick numbers that are relatively small. I'm not going to pick an x value of like 10 to plug in here, because before long, when I start plugging 10 in, 2 times 10 is 20, minus 1 is 19, right? I'm going to get some value that's way off of my table. I'm also not going to pick values like 15 because it's already off of my graph. Okay, now, I have a favorite 5 that I pick whenever I can. And I say whenever I can, technically I can whenever I want. But if I'm going to keep this simple for me, there's some other things that I'm not going to concern you with yet. But usually I pick the same 5 values for my x's. And they fit the category that I just described. Some positive, some negative, and they're small and easy to plug in. Here's my favorite 5 to plug in. I'm going to use -2, -1, 0, 1, and 2. Some negative, some positive, and they're all relatively small. Could I have picked 0.5 if I wanted to? Yes. Would I want to? No. Because I don't like graphing things that have decimals in them. I don't know about you guys, but I find it easier to graph whole numbers, don't you? So, let's go with that. Now you might say, Mr. Tompkins, what do you do to find your y value then? Well, remember the other day when we practiced being able to evaluate a function? That's what you have to do. How many times do you have to do it? 5 times. I'm not going to show this to you 5 times all the time, but I'm going to show it to you here to begin with. What I'm going to do is I'm going to take this equation, y equals 2x minus 1. You're choosing the x value. You're finding your y value. And when I say finding, you're going to find it because you're going to plug in your x. So I don't know what y is, but what's the first x value in my table?
2.
-2. So I'm going to plug -2 in for x. And I'm just going to simplify all the ordered operations to figure out what y is. So I'm going to begin by multiplying 2 times -2, which is -4. Then I'm going to take -4 and subtract 1, and I'm going to get -5. So with this value of -2, my y value is going to be -5. Because that's what I got out for y when I plugged the -2 in for x. Okay? If you guys don't copy down a couple of these, you're not going to have any idea how you completed your table. So I would expect this to like be showing up somewhere in the middle here. Again, you're doing this technically 5 times. Okay, there's the first one. What's the next value I'm going to have to plug in? We're going to plug in the next value, which was -1. Y equals 2 times -1, and then -1. Again, we're just following the order of operations here. So what's 2 times -1? 2 times -1. -2. And what's -2 minus 1? -3. So when you plug in -1, you get out -3. And just continue. Plug in 0. 0 is my favorite number to plug in because it doesn't get much easier than that. 2 times 0 is 0. 0 minus 1 is -1. There's my next value. Okay, then we repeat again and we plug in 1 and we plug in 2. So if I plug in 1, what's 2 times 1? 2. What's 2 minus 1? 1. There's the next value in my table. Plug in 2. What's 2 times 2? 4 minus 1 is 3. Delaney. You can, yes. I'll be honest, this is what I would call my side work. Okay? What you need to show is what you need to show. Some people are going to show it every time. Some people are going to plug it in, and that's fine, whatever works. But I expect your table to be complete when you're done.
You don't have to show it on the test.
No, you don't have to show all that on the test. Quentin.
Aren't you just adding 2 for y?
Well, it depends on what I'm doing for x. If I would have plugged in 7 for x, would I have just been adding 2? Okay, so again, it depends on what I'm doing for x. Now, take your 5 ordered pairs, okay? Because remember, this is an ordered pair here. -2, -5, right? This is an ordered pair of -1, -3. This is an ordered pair of 0, -1. The ordered pair of 1, 1, and the ordered pair of 2, 3. Take your 5 ordered pairs and graph them now. And here's my hint. What should it look like when I'm done? It should look like a line. Now, how many answers did we actually say there were to these particular equations? There were an infinite number. Right now on my graph, how many have I shown? I've only shown 5. So here's the last part of this. It's the easiest part, but it's also maybe the most important part. You need to take your 5 points, which we just agreed that should be on the line, and you need to connect them with the line. Now, when it comes to your assessments, I'm going to give you a straight edge. Okay, but you guys right now can utilize something that is straight and flat. Okay, I'll give you a ruler, but with this short of time, I'm going to pass them back and then collect them right back. Yep. Or your ID is another one that people like to use all the time. Yes, you do, because you're going to show that that goes on forever and ever and ever. That's a great point. So we're taking all 5 of the points that we've graphed, and you're going to join them together with a line. And because this line continues up and down forever, we need to make sure that we include arrows on each side of that graph. Now again, what is this line showing? This line is showing every number is a solution to this equation here. So I'm going to show you this. This is kind of cool. If you were to continue on this line, this point right here is on my line. And this point right here is the ordered pair of 4, 7. Well, if I put 4 in for x, what's 2 times 4? 8. What's 8 minus 1?
7.
There it is. You're also showing other values, other than just these 5. You're showing other values that make that equation true as well. Okay? All right, questions on example 2a. I got one more that I want to try and get through here. Okay? Example 1b. Here's where you need to be a little careful. Okay? Here, there is a number physically written in front of you, the x, that was a 2. Okay? On the second one, there's not a number physically written there. But what is it implied to be? A -1. So if you need to write that -1 in there, then do so. But you need to know that that's a -1 there. Okay? Now, here's the thing. I see no reason that I can't choose the same 5 values that I just chose before. So when I got to create my table, I am going to go with -2, -1, 0, 1, and 2. Will I always choose those 5? No. We'll talk about tomorrow when I wouldn't. But for right now, those are the 5 values that I'd like you to get in the habit of doing. Now, figure out what your y's are. Go. You got to plug all those in and figure out what all the y values are. Okay, and the nice part is when you go to create or check your table, you're going to graph your points and you're going to see if they all end up on the same line. Because they should, since this is linear. Yep, if you think you've got your table made, double check it there with your graphing of it. Well, I gave you that for part of your homework. You're going to need graph paper tonight. Again, you're going to take all of your x values, you're going to multiply it by -1 first. After you multiply it by -1, then you're going to add 4. Your table should look, if you chose the same 5 values I did, your table should match my table. Do our tables have to be identical? No. Do our graphs need to be identical? Yes. That's the weird part. We may have different tables, but our graphs had better look the exact same. Okay, so when I get done, I'm going to graph my 5 points. I'm going to grab a straight edge, draw a line that goes through all of those 5 points, and put arrows on each side. And that is all of the ordered pairs that will make that equation true. All right, so for your homework tonight, some of this, there's 2 examples. Okay, some of them are determine whether or not this is a solution. You're going to need to do that on your own paper. When it asks you to graph, I provided this. I do expect to see a table for every one of your graphs that go with it. Okay? So for your homework tonight, we have page 410. Numbers 1, 3 through 7, and 12 through 17. All right, this is a rather large lesson. You'll notice that there's actually 3 pages of notes that go with this. We're going to get into page 3 tomorrow.